This is the lecture for Tuesday, September 18th. We're going to talk about motion in two dimensions, as well as relative velocity. So let's get started. First thing, motion in two dimensions. So we could go up to 3 dimensions as well, but showing 2 dimensions shows you all the new stuff. So let's suppose a particle. This particle moves as shown. I'll make a plot from some initial position Ri to some final position Rf. Okay, here's Ri. Let's say Rf is somewhere over here. And it does some sort of a trajectory like this, going through these points. And so these are the positions Ri and Rf. The displacement from the initial to the final is going to be the difference between the two. So the displacement delta R is equal to final, R final minus R initial. When I think of the displacement, I think of the change in the position. So you might find it convenient to actually think of taking Ri plus delta R. So the way I think of it is, this is the initial position, Ri. You make a change of delta R, and that's what gives you the final position. So therefore delta R is R final minus R initial. Okay, so if I think of it that way, then I have my positions. Here's my Ri, here's my Rf, and then delta R is the additional piece I add to Ri to get Rf. Okay, so you already know this. It's just good to review that. Now, we're going to talk about these things in terms of components. So in terms of the x and y components, this is x and y. In terms of components, the components of Ri are xi, comma yi, the x component and the y component. If I'm talking about our final would be x final, comma y final. Then delta R, which will have components delta x, comma delta y. This will be the difference x final minus x initial, y final minus y initial. The average velocity is defined as V average, and that will be delta R, the displacement over delta T. Displacement we just defined, divided by the time interval. By the way, if you have any questions, go ahead and ask my student who's supervising this lecture, and he'll stop the video and answer your questions. If I'm interested in the instantaneous velocity, then I take delta t to be the limit as delta t goes to 0. The instantaneous velocity is going to be just plain v, and that's the limit as delta t goes to 0, delta r over delta t. And that's just the derivative dr dt. Now, the meaning of these things in terms of components, we just say V average is equal to the average x component, the average y component, and then we take the x component, the y component of this side of the equation. So we will have delta x over delta t, delta y over delta t. If we want the instantaneous velocity, the components of the instantaneous velocity are dx and dy. And then if we take the right-hand side, the x and y components would be dx by dt and dy by dt. So we just treat each component separately. All right. Hopefully this is kind of straightforward. If you have any questions, once again, ask the student who's supervising the lecture. Now, I can write down, okay, so in my lecture notes, I actually write it down explicitly once again. If I'm looking at component by component, then V average x is equal to delta x over delta t. V average y, oops, you can't see that. V average y is delta y over delta t. And the x instantaneous is dx by dt, and dy is dy by dt. Now, sometimes in a lot of other contexts, it's these writing these AVGs are kind of annoying. So sometimes it is more convenient to write Vx bar. So that's a standard notation. That's not a vector hat. That's just a plain old bar on top. Vx bar is defined as average velocity x component. Vy bar again bar is V average y, and if you want, we can have this kind of unusual notation where you put a bar over the vector, and that would be the average of the vector. Okay, it's just another way of writing averages. Okay, now we can also define the average acceleration. And the average acceleration, AVG, is delta V over delta t. So this is the change in the velocity. So when I just say plain velocity, I mean by default the instantaneous velocity. And delta t is the time interval. Okay. Again, if you have questions, ask the students supervising the lecture. Then if I'm taking the components of the average velocity, then I have a AVG x component, a AVG y component, and this will be the x and y components of the change in velocity over delta t. So I will have delta Vx over delta t. What's the y component? It would be delta Vy over delta t. Again, if we want to use this bar notation, maybe you prefer that, then I can write a vector bar for the average and then I'll have the average acceleration x component, average acceleration y component, and that will be equal to the same thing I have here, delta Vx over delta t, delta Vy over delta t. If I want to go to the instantaneous acceleration, then I take delta t to 0, that limit, and the instantaneous acceleration is going to be plain old a will be the limit as delta t goes to 0, delta v over delta t, and so that will give me the time derivative of the velocity. Again, what this means in terms of components is just A has components AX and AY, and then I have dV x by dt, and then dV y by dt. So we just treat each component separately. Treat. Okay. If you wanted to see that written out explicitly, if you're still a little shaky on this, I can write this: the x component, average velocity, average acceleration is delta Vx over delta t. The average y component of the acceleration is going to be delta dy over delta t. And then for the instantaneous accelerations, I have dvx by dt, and ay is dvy by dt. Okay, let's do an example. Let's see if we can understand what's going on. Suppose the position of a particle is some position vector r, which is a function of the time, t, and that's equal to, I'll write in terms of components, 6t squared, comma 5t minus 2, where t is in seconds, and components of r are in meters. And the question is, what are the instantaneous velocity components Vx and Vy at time t is equal to 3 seconds. Okay. I will stop the video now, and you can work it out before we go over the solution.